Something hit Earth's atmosphere over the Barents Sea in February 2025, and the government satellites that track ballistic missile launches picked it up. It was moving at T-59 kilometers per second. The escape velocity from our solar system, the speed something needs to leave the sun's gravity behind for good, is about 42 kilometers per second. Whatever burned up over the Arctic that day was moving too fast to have come from anywhere near us. It came from somewhere else entirely, another star system drifting through the galaxy for who knows how long before it happened to end its journey in our atmosphere. And it wasn't the only one. Researchers running the numbers in a study published in early 2026 concluded that right now, at this exact moment, there could be on the order of tens of millions of interstellar objects moving through the volume of space inside Earth's orbit around the Sun. Not out past Neptune, not in the distant Kuiper Belt, inside the orbit where Earth itself lives. That estimate comes with real uncertainty attached to it, and it's worth being upfront about that uncertainty from the very start. But even the low end of the range implies our solar neighborhood is far more crowded with visitors from other stars than anyone assumed even a decade ago. And that's just the backdrop. Because 3I Atlas, the giant interstellar comet that tore through our solar system in 2025 and left scientists genuinely startled by what they measured, has been handing over data ever since. Some of what that data shows, published in peer-reviewed journals within the past several months, ranks among the strangest chemistry ever read off any object in the history of modern space science. Let's build this properly, because understanding why this moment matters requires understanding just how fast the picture changed. For nearly all of recorded human history, we had never confirmed a single object from another star system passing through our solar system. Not one. Space is enormous, these objects are small and fast, and for most of history, our telescopes simply weren't sensitive enough to catch something moving at that speed, at that distance, before it was already gone. Then, in 2017, Oumuamua showed up, a strange, elongated shape, no visible tail, and a small but measurable acceleration that took years of debate to even partially explain. Scientists argued about what it actually was for a long time afterward. Then, in 2019, Borisov came through, looking and behaving much more like a conventional comet, giving the field a bit of a sigh of relief that the universe wasn't going to keep sending confusing outliers. 2. Confirmed interstellar visitors in 2 years, after 0 in the entirety of recorded human history. That alone should have told us something important about how common these objects actually are compared to what we'd assumed. Then, in July 2025, everything changed again. Early that month, a third interstellar interloper was discovered, first catalogued under a temporary designation before being confirmed as interstellar in origin and rechristened 3I Atlas. The Atlas Survey Network in Chile, the same system that scans the sky nightly looking for asteroids that might threaten Earth, caught a faint, fast-moving point of light on July 1st, 2025. Within days, astronomers had computed its orbit, and the orbit said the same thing Oumuamua's had said 8 years earlier. This thing is not from here. But 3I Atlas turned out to be different from the first two in ways that immediately made astronomers uneasy. All of the field's preparation for the next interstellar object had essentially been preparation for something that behaved like Oumuamua or something that behaved like Borisov. This didn't look like either. Crazy and exciting, in the actual words of one professional astronomer studying it, not a phrase from online commentary, but language that made it into the scientific discussion around the object. The first difference was speed. 3I Atlas was moving at roughly 130,000 miles per hour, dramatically faster than either of the two previous interstellar objects, fast enough that it had clearly been traveling through the galaxy for an almost incomprehensible span of time. Estimates put its journey at somewhere in the range of 10 to 12 billion years before it ever came near the Sun. 10 to 12 billion years. Earth itself is about 4.5 billion years old. This object had already been drifting through interstellar space for longer than our entire planet has existed. It was ancient before the first single-celled organisms figured out how to divide on the surface of a young Earth. The second difference was size. Oumuamua was roughly the size of a football field. 3I Atlas is an entirely different scale of object. Hubble Space Telescope observations constrained the diameter of its icy nucleus to somewhere between roughly 4 to 400 feet and as much as 3.5 miles across. That size created an immediate statistical puzzle that Harvard astrophysicist Avi Loeb raised almost as soon as the numbers came in. Based on how populations of objects like this are expected to be distributed, with small objects vastly outnumbering large ones, you'd expect to detect something on the order of 100,000 Oumuamua-sized objects before you ever happen to detect something as large as 3I Atlas. Instead, We jumped from one small object in 2017 almost directly to something potentially enormously more massive. That doesn't fit cleanly into any distribution astronomers currently model for how these objects should be sized and how often each size class should appear. Something about our assumptions may need revising, though it's worth noting plainly that this kind of statistical tension, while genuinely interesting, is also exactly the sort of thing that tends to resolve itself as sample sizes grow. 3 data points is a very small basis for confidently declaring a population distribution broken. Once the object was confirmed as interstellar and clearly unusual, science teams pointed essentially every major telescope on and above Earth directly at it. The James Webb Space Telescope, Hubble, the Subaru Telescope in Hawaii, the ALMA Array in Chile, and even NASA's Europa Clipper spacecraft captured observations during windows when ground-based telescopes were blocked by the sun's position. More than a dozen. Separate NASA assets alone gathered and processed imagery of the object. What came back over the following months produced paper after paper, each adding another layer of genuine strangeness to an already extraordinary find. The water chemistry is where the loudest reaction in the scientific community came from. Every comet ever studied within our own solar system contains water, and that water carries a specific ratio of ordinary. Hydrogen to deuterium, the heavier isotope of hydrogen, carrying an extra neutron. That ratio functions almost like a chemical fingerprint, telling scientists something about the temperature and conditions under which the object originally formed. Across every comet we've ever measured in our solar system, that ratio stays within a fairly consistent range. A study led by researchers at the University of Michigan found something far outside that range in 3I Atlas. Extraordinarily elevated levels of deuterium relative to ordinary hydrogen in its water, more than 10 times higher than any comet ever measured in our own solar system. Roughly 1 deuterium atom for every 100 hydrogen atoms in the water around 3I Atlas. The carbon isotope ratios measured alongside it also exceeded typical values seen in solar system comets, and even in nearby interstellar clouds, and the protoplanetary disks thought to form other planetary systems. Both the water chemistry and the carbon isotope signature sit well outside anything previously observed in our own cosmic neighborhood. What that suggests, according to the researchers who published these findings, is that the physical conditions that shaped our own solar system may be genuinely different from how planetary systems form and evolve. Elsewhere in the galaxy, we are not necessarily looking at a universal template. We may be looking at real chemical evidence that other planetary systems form under meaningfully different physical conditions than the one we happen to live in, conditions we've never had direct access to before this object arrived. And the water was just the beginning. Then came the methane results. The James Webb Space Telescope detected unusual chemistry throughout 3I Atlas, including the first direct detection of methane ever made on a visitor from another star system. The methane wasn't just present, it was present in a quantity that made researchers pause and double-check their instruments. The measured methane to water ratio came out roughly 11 times higher than any previously measured solar system object. 11 times higher than any comet we've ever studied at home. The deuterium enrichment within that methane was even more extreme than what was found in the water, coming out to roughly 1 deuterium atom for every 30 hydrogen atoms in the methane molecules around 3I Atlas. The most sensitive infrared instrument humanity has ever built was reading chemistry off a passing interstellar visitor that simply doesn't match anything in any solar system body we've ever cataloged. Whatever 3I Atlas is, it isn't just an unusual comet by our own solar system standards. It appears to be a comet that formed in a fundamentally different chemical environment than anything nearby. Then came the search for a signal, because when an object this unusual passes through your solar system, the natural next step is pointing the most powerful radio telescopes on Earth directly at it and listening. A narrowband radio technosignature search. Targeting 3I Atlas was carried out using the 500-meter aperture spherical radio telescope in China, the largest radio telescope on the planet, across 4 separate observation windows between October 2025 and January 2026. No credible narrowband radio technosignatures were detected after careful analysis. No transmission. Nothing resembling deliberate technology broadcasting on radio frequencies. The SETI Institute independently ran its own search using the Allen Telescope Array and came back with the same result: silence. It's worth being precise about what that silence actually means and doesn't mean. The absence of a detected radio signal tells us 3I Atlas isn't broadcasting to us on the frequencies we checked. It doesn't, by itself, prove the object is entirely natural, but among most working astronomers, a body whose shape, outgassing behavior, and spectroscopy are broadly consistent with an unusually large, unusually old, chemically unusual comet combined with total radio silence, reads as strong evidence for a natural object, not as an open mystery still pointing towards something artificial. That distinction matters because it's exactly where the more sensational interpretations of this object tend to diverge from where most of the field actually lands. Avi Loeb's public position throughout 2025 and 2026 has been that these anomalies deserve to be taken seriously rather than dismissed too quickly, and he's continued raising specific numbers to make that case. He's pointed to the object's path lying within just a few degrees of the ecliptic plane, the flat disk in which the planets orbit the sun, calculating the odds of that alignment happening purely by chance at somewhere around 1 in 500. He's noted its size implies a mass roughly 1,000,000 times greater than Oumuamwa's. He's also raised a claim about its composition potentially. Containing nickel with comparatively little iron, a ratio he's compared to certain industrial alloys used in aerospace applications, though this specific compositional claim is considerably more contested within the field than the water and methane measurements, which were independently confirmed through peer-reviewed spectroscopy from multiple telescopes. It's genuinely important to separate these two categories clearly. The unusual deuterium ratios, the elevated methane levels, and the sheer size and age of the object are measurements, confirmed independently by multiple instruments, and published through standard peer review. The interpretation that these anomalies, taken together, suggest something beyond a natural, if chemically unusual, comet, is Loeb's own framing, and it's one that a large portion of the working astronomy community has been fairly consistently skeptical of, the same way much of the field pushed back on his earlier possible artificial origin arguments about Oumuamua years ago. That skepticism doesn't mean the data itself isn't remarkable. Even the most conservative reading of these measurements describes a genuinely unprecedented object. It just means the leap from unprecedented natural chemistry to possibly not natural at all is a much bigger leap than the raw data alone requires, and it's one specific scientist's interpretive lens rather than a scientific consensus. While all of this was unfolding around 3i Atlas itself, as it rounded the sun in late October 2025 and began heading back out past Jupiter toward the outer solar system, and eventually back into interstellar space, something else was quietly being calculated in the background. A study published in February 2026 by Avi Loeb and a postdoctoral researcher working from an entirely different data set arrived at a number so large that most people who first heard it assumed it had to be an error. An estimate of roughly 35 million interstellar objects currently occupying the volume of space inside Earth's orbit. The methodology behind that estimate is worth explaining because it's genuinely clever even if the resulting number carries substantial uncertainty. The US government maintains a database, often referred to as the CNEOS Fireball Catalog, populated using the same military satellites built to detect ballistic missile launches and nuclear detonations. Whenever an object burns up bright enough in the atmosphere to register on those sensors, the event gets recorded, its velocity gets calculated, and the data is eventually declassified and made public. A rock, only a few meters across, colliding with Earth's atmosphere at high speed, generates a fireball with an energy release comparable to a small nuclear detonation, easily detectable by satellites designed to watch for exactly that kind of flash. Loeb and his colleague went through that public catalog, specifically looking for meteors that had entered the atmosphere moving faster than the solar system's escape velocity, since nothing gravitationally bound to the sun can exceed that speed. Anything moving faster has to have come from outside. They found two clear candidates in the catalog's recent history, one detected in July 2022 over the eastern tropical Pacific, exceeding escape velocity by a wide statistical margin. Another detected in February 2025 over the Barents Sea in the Arctic, the same event mentioned at the start of this piece, also comfortably exceeding escape velocity. A third candidate, detected in April 2026 over the South Atlantic east of Argentina, showed a velocity component well above the roughly 42 kilometers per second needed to escape the sun's gravity, with the interstellar origin confirmed at an extremely high statistical confidence level. From those confirmed interstellar meteor detections spread across several years of catalog data, Loeb calculated an implied collision rate of roughly 3/10 of one such event per year. He then worked backward through the geometry of Earth's cross-sectional area moving through space and its orbital speed to estimate how many similar objects would need to be present in the surrounding volume of space to produce that observed collision rate. The resulting estimate, something on the order of tens of millions of meter-scale interstellar objects, currently occupying the volume inside Earth's orbit, together adding up to an enormous total mass of interstellar material quietly passing through our solar neighborhood at any given time. This kind of extrapolation, working from just 2 or 3 confirmed events to estimate a population of tens of millions, carries real statistical uncertainty. And it's the kind of estimate that will almost certainly get refined, likely downward in confidence interval, if not necessarily in central estimate, as more data comes in. But the underlying point holds, regardless of exactly how the final number shakes out. The solar system is not the sealed, isolated bubble it was once implicitly treated as. It's porous, constantly threaded through by material from other star systems, some pieces the size of mountains, some the size of a car. Most of it never noticed at all until the right instrument happens to be watching at the right moment. And that brings us to the actual news of 2026, the part of this story that changes everything going forward. A new telescope just came fully online, and it's about to shift the discovery rate of these objects from roughly once-a-decade events to something approaching routine monitoring. The Vera C. Rubin Observatory in Chile, home to the largest digital camera ever built for astronomy, is designed to photograph the entire visible southern sky every few nights, generating a continuous time-lapse of the changing universe at a level of sensitivity that has simply never existed before. In its earliest operational tests, it demonstrated the ability to generate an enormous volume of alerts, flagging changes in the sky in a single night, everything from asteroids to distant cosmic explosions. Over its planned 10-year survey, current estimates suggest Rubin could detect somewhere between roughly 5 and 50 new interstellar objects. And if these objects turn out to be more common than the first 3 discoveries suggested, that number could climb considerably higher still. The uncertainty in that range is itself the honest headline. We genuinely don't yet know how common these visitors are, and Rubin is about to start narrowing that uncertainty, one confirmed detection at a time. Javi Loeb has already given a name, half in jest and half in earnest anticipation, to whatever Rubin discovers next. He's referred to it informally as the next interstellar Rubin object, before it's even been found. Beyond simply cataloging these detections, Loeb has proposed something more ambitious, preparing a small, fast-launch spacecraft ready to intercept the next confirmed interstellar object as it passes through, close enough to photograph it up close and potentially sample the gas and dust in its surrounding coma before it disappears back into interstellar space for good. Even in the most conservative, entirely natural object scenario, such an instrument could directly check whether the material carries organic molecules, the basic chemical building blocks associated with life as we understand it, something no telescope observing from a distance can definitively confirm. That prospect matters, given what's already been measured on 3i Atlas. We've confirmed methane levels roughly 11 times more enriched than anything found in our own solar system. We've confirmed deuterium ratios implying formation under conditions colder, older, and more alien than anything in our immediate cosmic neighborhood. The next time an object like this passes through, and based on Rubin's expected detection rate, that could plausibly happen within years rather than decades, we may finally have a real chance to study one up close with an instrument riding alongside it, rather than watching from millions of miles away through a telescope lens. There's one more number worth sitting with before wrapping this up. Interstellar objects like 3i Atlas move through our solar system at speeds several times faster than every human-made spacecraft that has ever left or is currently leaving our solar system. Voyager 1, Voyager 2, Pioneer 10, Pioneer 11, and New Horizons. The 5 fastest, farthest-reaching machines our species has ever built, decades of engineering pushed to the absolute limits of what's currently achievable, are all slower than the average interstellar comet simply passing through on its way somewhere else. That single comparison captures something genuinely humbling about where we currently stand. We are a civilization that has only just barely managed to throw a handful of small probes past the edge of our own star system, while objects from other star systems drift through our neighborhood on a regular basis, some of them burning up in our atmosphere as fireballs quietly logged by military satellites and counted eventually by scientists paying close attention. For the first time in the history of our species, though, we finally have an instrument sensitive enough to actually catch these visitors as they arrive, rather than only reconstructing their existence after they've already passed us by. 3i Atlas came, and it's already moved past Jupiter, heading back out toward the outer solar system, carrying its ancient chemistry, its unprecedented water and methane ratios, and whatever remains of its 10 to 12 billion year journey back out into the interstellar dark it emerged from. We had months to study it. Nearly every major telescope on Earth and in space was pointed at it at some point. And what we confirmed, carefully, through peer-reviewed measurement rather than speculation, is that the conditions that shaped it were meaningfully different from whatever shaped our own solar system, evidence that planetary chemistry across the galaxy is stranger and more varied than our single local example ever suggested on its own. The next one is almost certainly already out there, somewhere between here and Neptune's orbit, moving fast, ancient, unnoticed for now. Rubin is watching. The fireball tracking satellites are watching. The radio telescopes are listening. And for the first time, we're genuinely getting ready. No, just to catch a fleeting glimpse of a passing mystery before it disappears again, but to eventually intercept one, sample it directly, and ride alongside it for a few precious months before it escapes back out into the dark it came from, carrying whatever answers it holds about how differently things can form out there around other stars.